And I would like to remind you that today you are going to take the official photo of the conference. It's right after Oliver's talk. So please let's get together to take the photo. And it's my pleasure to introduce Oliver Lorscheid from the University of Groningen, that will speak about Lorentzian polynomial and matroid over triangular hyperfields.
Okay, next try. Good morning. Thank you for the introduction. Sorry for this malheur with the microphone. Yes, I will talk about this project about Lorentzian polynomial and matrix over triangular hyperfields, jointly with Matt Baker, June Ha, and Mario Kummer. Yeah, sorry, Kris, for stealing your place of the mini course, but it's actually quite related to their mini course, the lecture on Monday. So just pretend I'm Kris, and this is ramification of the Monday lecture.
Very easy.
Okay, so I don't assume that you're familiar with any of the words in the title, so I go easy for you today. Well, you have seen matrices. You get a third definition of matrices in the talk, but matrices are actually play a minor role in the background. They will come up here and there, but more about representations of matrices, as you will understand during the talk. So just please feel free to ask questions in between, and I hope to make things understandable. So you should slow me down, but I hope I go slowly enough for everybody. Let's start with some motivation around Lorentzian polynomials, which were introduced by June Ha and Peter Brandon as a tool to streamline and simplify several proofs in combinatorics about the log concavity of certain sequence of numbers which are counting different things. And I mean, June had this approach via Hodge theory in the beginning that he associated with representable matrices, and then he could abstract this to all matrices. And somehow, in the end, he reached, together with Peter Brandon, this notion of Lorentzian polynomials, which abstracted things, made things much easier. It's basically just linear algebra and analysis. There's no advanced theory like algebraic geometry or Hodge theory going on. And sometimes it's getting more general because you don't need this algebraic framework. You don't need to have certain varieties to exist. So somehow the definition of Lorentzian polynomials is very elementary. You can give this to a first-year student. But the hard thing here, I mean, there's machinery in the background, so certain hard proofs that Peter Brandon and June Ha did. But there's one hard thing. If you have a certain sequence and you want to use this machinery, you have to prove that the polynomial that the sequence forms is really Lorentzian. So it's hard in practice to decide whether a polynomial is Lorentzian or not. And this was a little bit the starting point of our project, and this is one of the main statements of our paper. The space of Lorentzian polynomials is a Grassmannian. And the catch here or upshot is that Grassmannians are easier to handle, and the Plücker relations are easier to verify than the defining equations for Lorentzian polynomials. Okay, if you look at that, by the way, I like this pointer, so you can just point it anywhere and go around. But so the catch here is that, well, I didn't tell you what the Lorentzian polynomials are, but there's a clear definition for those who know that. But it's a little more vague. What's a Grassmannian? What do I mean by that? I will explain this at some point in the talk. Another catch is this point, a word is. So I will explain what this word means in the talk, which is also not so clear. Okay, let's get started. So I start with Lorentzian polynomials, which were introduced by Brandon Ha in 2020. Around 2020, the preprint was out a year earlier. And I set up some standard notation that I use during the talk. So square brackets n is an element set, so I'm totally with Alex there. So I'm diverging from my Monday talk where I used the n+1 element set. Still pretend to be to Kris. n choose r, I mean square brackets n choose r, is the collection of r subsets of n. Then x to the I, where I is a subset of n, it's a variation on the multi-index notation. So it's simply the product of the x sub small I, where small I reigns over the elements of capital I. And then f stands in this talk for a polynomial with non-negative real coefficients in x1 to xn of degree r. It's homogeneous of degree r. The coefficients are, I denote by delta I, so this should remind you of the Plücker vector and the Grassmannian before, but we get to that later. So there's a suspense arc in this talk, which I tried to create. So there's a first hint of a Grassmannian in the notation. And this polynomial is of a very particular sort. So it's in each variable x small I, it's affine linear. It's of degree 1, or certain terms which have degree 0 in xi. And this simplification that one doesn't need, but I do it for the talk because it's easier. Like this, I talk about matrix. If I allow any kind of powers of the xi's, I have to talk about polymatrix, but I just don't want to do this here. So you get the gist of this work for a large part just with the simplification. Okay? And then with the simplification, I can just define very simply what's a Lorentzian polynomial. I mean, this polynomial f is Lorentzian if it's a log concave function on the positive orthant. That's it. And I mean, log concave, I've spelled it out for you. This means simply we take any line segment in the positive orthant with n's alpha beta, and if we evaluate the function log f in these endpoints divided by 2, then this is bound above by the value at any point on this line segment between alpha and beta, just like in usual analysis. Sorry? T is anything on the line segment. So T goes, if we vary T, we go from alpha to beta on this straight line. Good. Okay, here I want to tell you the first relation of Lorentzian polynomials with matrix, which was already clear to Peter Brennan and June Ha. So let me first give you a third definition of matrix, which is a definition that I use. But as I said before, this is a little bit in the background, so you don't need to internalize it. But I consider matrix as a set of bases, which is a subset of R subsets of N that satisfies the base exchange axiom. So whenever we have two bases I and j and m, and then we can exchange any element small I and I by some element j and j, and we get, again, a basis. So it's literally the same as the Steinitz basis exchange axioms for bases of vector spaces, and we pretend I and j are bases, and it satisfies this thing. If you come from the rank description from my Monday talk, then the bases are the minimal sets that assume the full rank. If you come from the polytope description of Alex's talk, then these are the vertices, the outer vertices of the polytope. So if you prefer something like that. But let me step back. Matrices are not so interesting. We talk about matrix representations in this talk. So the first kind of representation is a point in a complex Grassmannian. I mean, C could be any field for that purpose, but I stick to C because this comes up later again. Oh, sorry. This shouldn't be there yet. So we can define the support of a Plücker vector as all those R subsets I for which the Plücker coordinate doesn't vanish. And then this collection is a matrix, and this is called a representable matrix, or more specifically, a complex representable matrix. As we heard before, I think in Alex's talk, not every matrix is representable. In fact, almost all matrices are not representable. But this is still kind of a rich source of matrices that appear. For Lorentzian polynomials, something similar is true. They also represent matrices, and it's even better. they represent all matrices. So every matrix representable as a Lorentzian polynomial in the following sense. So if we have a polynomial f with non-negative real coefficients, then we define the support of f as those I for which the coefficient delta I doesn't vanish. And then it's a fact that was proven in Brennan Huss' paper that a subset of n choose R is a matrix if and only if it's a support of a Lorentzian polynomial. So this actually gives us a redefinition of matrix. So matrix is a thing that's a support of a Lorentzian polynomial. And that's maybe the right way to think of it for this talk. But it's intimately, I don't know why this happens. Somehow the slides flip without me wanting it. So what I want to say is matrices are intimately related to Plücker vectors. So this is maybe the essence that we should carry away, and at some point later I will make this precise. Okay, there's a different characterization of Lorentzian polynomials which makes it easier to compute with them. So to say, to determine whether such function is log concave or not, this seems like an elusive property. How do you get your hands on that? And so we go back to the original, well, this is not the original definition, but close to the original definition of Brennan-Haar of a Lorentzian polynomial, and it turns out to be equivalent. So Lorentzian polynomials can be characterized in terms of derivatives, which I don't say precisely what it does, but it reduces the degree of a Lorentzian polynomial to degree 2. And we need to take all sorts of partial derivatives. And then we look at the determinants of the Hessian matrix of this degree 2 polynomial. And these determinants decide whether this matrix has a Lorentzian signature, which is the condition to be a Lorentzian. So Lorentzian signature means precisely the Hessian is a limit of invertible matrices with exactly one positive eigenvalue. So it's actually a limit of Lorentzian matrices, or, I mean, it's normally Lorentzian physics is exactly one negative eigenvalue, but well, they flipped that convention for a specific reason. It has to be like that. And here is an example, which will be the running example for this talk. We take polynomial, it's a case R equals 2 and n equals 4. So we can take 2-element subsets of the 4-element set. And this polynomial of degree 2, so I don't need to consider partial derivatives of this. And I can look immediately at the Hessian, which is displayed here. Note the diagonal is 0 because we don't have squares in there. And it turns out that this has a Lorentzian signature if and only if the determinant is non-positive. I don't explain how this goes in detail, but there's something called Cauchy interlacing for eigenvalues of matrices, which relates to the signs of the principal minors of this matrix. And turns out that the signs of the proper minors of this matrix already have the right sign. So we only have this one condition, one determinant condition, which is polynomial of degree 4. We'll come back to this later. But this is an exact characterization of Lorentzian polynomials in terms of this degree 4 polynomial. Okay. So next step, we're going a little bit back in history. And I mean, I'm always happy if I can relate to some older literature, which normally is in the last half of last century maybe, but this is by far my personal record. So we go almost 2,000 years back to Heron's formula. And this is the formula for the area of a triangle. So we have a triangle with side lengths ABC, and then the area can be expressed as square root of a certain degree 4 polynomial delta of ABC, which is 2 times the products, the sum over the squares of 2 of the 3 numbers ABC minus the sum over the 4th powers of the 3 numbers. So it's Heron's formula. Somehow implicit in there, you see that to make sense of this formula, delta of ABC has to be positive for a triangle, right? Otherwise, this wouldn't make sense. So implicitly, this was already known. Something that we use, I don't know if, I mean, this must have been known before, but this I didn't find anywhere. It's a very simple lemma. The non-negativity of delta actually characterizes triples ABC which form a triangle. So it's this lemma, and since it's so simple, I want to show you a proof. So by symmetry, we can assume that C is the largest side, and then ABC form a triangle if and only if C is bound above by A plus B. And then I use this factorization of delta in 4 linear factors, which you can check by hand. And the first 3 linear factors are non-negative by assumption, and then the non-negativity of this last factor is equivalent to this inequality here. End of proof. Okay, I just found this argument cute, so I want to show it to you. But the important thing is that this lemma really determines the area of triangles by an algebraic inequality. So the set of triangles, it's a semi-algebraic set. Here's a picture for the slice where C equals 1, so I can bump it down a dimension. And it's this area inside a tilted parabola. I mean, if you figure out it's really parabola, the boundaries of degree 2, even though delta's of degree 4, but I guess it's because of square root, but yeah, I mean, anyways, so any question, by the way, you should interrupt me with questions if you have questions, otherwise I go on. Let's,
just a small
yes.
Usually, I think delta is defined, I have seen it as the product of those.
Yeah, it might be. It's the same thing.
Yes, yes.
Yeah. Okay, so let's get back to our example and link this to the lemma that we've just seen. The link is very simple. So here's a Hessian of our degree 2 polynomial with 4 variables. And then it turns out that the determinant of this matrix is minus delta of 3 numbers A, B, C, which are the square roots of the product of 2 of these deltas. And you note here with the indices that these 3 terms have the indices 1, 2, 3, 4 in some permutation. And well, this should remind you of something. So the suspense arc is slightly increasing for those who know Grassmannians. But for now, this just means that using the lemma from before, that the non-negativity of delta characterizes triangles, and that the non-positivity of the determinant of HF characterizes Lorentzian polynomials, means that this polynomial here is Lorentzian if and only if these 3 numbers form a triangle. So it's kind of a funny characterization of Lorentzian polynomials of this form. But this already is the jumping point for the next ingredient that I want to show you, which goes back to Weir's approach to tropical geometry, who uses so-called triangular hyperfields. I get to that in a moment. First, I want to give you an intuitive idea. So this is back in our century, developments from the early 2010s. So what I want to explain you is março of dequantization in an example. That's basically what we have seen in Kris' Monday lecture, but I phrased it a little bit different. So it considers example X, which is the spectrum of C joined 3 variables whose sum is 0. So, and I consider the absolute value, the usual absolute value from C to R, or R greater equals 0, elevate to some power Q, where Q is any positive real number. Could be 1 to ease thinking, but later I want to vary Q and take the limit. Q goes to 0. And then the set of C rational points of X, which are all triples ABC, whose sum is 0, its subset of C cubed, is mapped under this map to this calligraphic Q of X, which are all triples of non-negative real numbers whose Q squares form a triangle. Think about it for a moment. This is maybe my point where I should go to the blackboard to give you some idea. So we have A, B, C, which sum to 0, and they form a triangle. And that's a proof that the image is contained in AQ of X. It's actually equal to the image, so it's surjective onto there. This is something that I call Q amoeba of X. It's closely related to what Kris called an amoeba in the Monday lecture. I'll show you a picture in a moment. And this fact extends to the Hausdorff limit of all this AQ of X's. There's an X missing. And this is by definition, or by one definition, the tropicalization of X, which are also denoted by A0 of X. And these are all triples ABC, for which the maximum between the three numbers appears at least twice. Okay, this is all no news to us, but it comes in a slightly different formulation. So the thing that Vero did is that he identifies these sets with varieties over certain hyperfields. And this is what I want to explain to you. But there's one thing that I want to curve around. So there are a lot of cool hyperfields out there, and they're very useful. But if you look at the collection of hyperfields, they form one ugly category. So I don't want to go into that, but use some other framework, which are bands, which I come to in a moment. But first, let me give you a picture. So question to you. There are some certain parts of the pictures that you have seen before. So who recognizes something in this picture? So I give you a moment. So this here are different amoebas, where again, the slice C equals 1 for different parameters. So Q equals 2, Q equals 1, 1/2, and then the limit Q equals 0, which is the tropicalization. And here's a kind of picture as it's drawn usually in tropical geometry, taking logarithmic coordinates.
Q equal to 2, you sure? Q equal to 2?
Yeah, good. This was Q equals to 2. This is precisely the picture that I showed you before, but a little zoomed in, that I can show the behavior before. This agrees with the locus of triangles. Yeah. And the other pictures that you have seen, I said it already, so it might be too trivial. Yeah, William.
For Q equals 1, you get the absolute value.
Yeah, this is precisely the picture that we saw in the Monday lecture.
And for Q equals 0, you get the limit as t, well, applying the logarithm. No, actually, I don't know what the picture for Q equals 0 is.
Yeah, the pictures that we have seen is, well, if we take logarithms of the coordinates, we get from this rectangle shape to what Kris calls the amoeba, which we have seen, and then here's this Linus tropicalization that we saw in the Monday lecture. So, good parts of these images were already covered before, so that you can link ideas. Okay, let's do bands. So bands, it's again recent development. This was introduced by Matt Baker and Tongjin myself last year, so it's about to be published, so I put round numbers there. It's an effort to simplify blueprints that are used before, which are more general, but bands are more geared towards applications in matrix theory and so on, and they're a little simpler to digest. So I can give you a 2-minute definition of bands in the following, which I hope you appreciate. So let's start with the question, what is a ring? We all know what's a ring. Well, the ring in algebraic geometry, unital with commutative. So this is a commutative semigroup R with multiplication together with certain constants, 0, 1, and -1. And then it has this funny operation, which is an addition, and which satisfies certain axioms that I'm sure everybody can complete here. A band is a similar thing. So it starts the same. It's a commutative semigroup, B for band, with multiplication, constant 0, 1, minus 1. And then instead of addition, I take a set NB, the null set of the band, which are formal sums of elements of the band, which you should think of sums that are equal to 0, but these are just formal expressions, so that certain axioms are satisfied. So the first two axioms are kind of just reasonable axioms which are not doing much. So we want 0. The first axiom is how the constants operate. So 0 multiplies everything to 0. 1 is a neutral element for multiplication. Then the second property says that NB is an ideal, the semi-ring of formal sums. More explicitly, it's written down there. It contains 0. And it's closed under multiplication by B and addition. And third axiom, this is very specific to the purpose that we need. This basically says we have a notion of additive inverses. We cannot add elements, there's no addition, but we can say when elements sum to 0, and we can say what's a multiplicative inverse of an element. And this is phrased in this way that A plus B is in the null set if and only if B is a multiplicative inverse. So B is minus 1 multiplied by A. So the null set determines what are additive inverses. And then I throw in a second word, attract. Attract is something like a field for bands. So every non-zero element is invertible and 0 is not equal to 1. Here's just first sanity check. Every ring is a band. Just by replacing the addition by the null set NR, which are now formal sums of elements that really add up to 0 in R. And we don't lose information. If you have a band that comes from a ring, we can recover the addition by saying C is equal to A plus B, if and only if A plus B minus C is in the null set. So we don't lose information. So if I talk about morphism on the next slide, we get a fully faithful embedding of categories, and things behave quite nicely. But bands allow us now to talk about more exotic objects. And the first thing that I want to show you are triangular hyperfields that I mentioned before. So triangular hyperfields come with a parameter Q, which we saw before. It's a positive real number. And this is the tract TQ, whose multiplicative monoid are the non-negative real numbers, just with usual multiplication, constant 0, 1. Minus 1 is equal to 1 here. And more interestingly, the null set, this is given by formal sums of elements whose Q's square root form a polygon. So if you take sums with 3 elements, A plus B plus C, it just says the Q square root of the 3 numbers form a triangle. That's why it's called triangle hyperfield, but then we have to extend it to higher sums. And basically the fact that's behind here is that every polygon can be triangulated, so we can scale things back to triangles in a way. But yeah, that's the incarnation of the triangular hyperfield as a tract or as a band. If we take the limit Q goes to 0, and this is now the Maslov quantization that Vero talked about in the language of hyperfields, but it's the same thing, then we're getting smaller and smaller null sets, and the intersection of all null sets defines the tropical hyperfield, which is, well, the same multiplicative monoid, minus 1 is 1, and the null set now is the intersection of all these guys upstairs, and the condition turns out that the maximum is assumed at least twice. So it's a tropical equal to 0 condition. Okay? 2 more ingredients, and then I come back to the amoebas and tell you how to see them as varieties. A band morphism, it's a structure-preserving map. So you do the obvious thing. Well, it's a map from between two bands, B and C, that preserves multiplication, preserves the constants, and preserves null sums by applying the morphism to each element in the sum. And then the important example of a band morphism for us is that the absolute value to the Q is a morphism, a band morphism from C to this Q triangular hyperfield. It's just the same thing that we had before. If we have A plus B plus C is equal to 0, then the Q square roots, I mean, if we take absolute values to the Q square roots of these numbers form a triangle. Yes?
This is to see how the first condition that the A1 to AN from a polygon translates to the maximum appear twice. Is it easy to see?
Yeah, if Q gets smaller and smaller, you take the triangular inequality, C is less or equal to A plus B, and then if you take Q's root and Q gets smaller and smaller, then the values of A, B, and C have to be more and more equal. One value can drop and be slower, but it's an exercise, so maybe let me not do this now in words. Yeah, it's easy to see.
Sorry, just a quick
Yes.
question. You have here complex numbers with absolute value in all. Doesn't this situation generalize to any field with a multiplicative seminorm?
Yes. I mean, here, this is something particular. So you should look at this here. So this works for all Q greater or equal 0. It also works for 0. And for 0, this becomes the trivial absolute value. And then it says the trivial absolute value from C to the tropical hyperfield is a band morphism. And this generalizes to every non-Archimedean field or every non-Archimedean seminorm, which becomes a morphism into the tropical hyperfield. Yeah, that's correct. And it's an if and only if. So a map from a ring into the tropical hyperfield is a band morphism if and only if it's a non-Archimedean seminorm. Okay.
First definition of this you said, this quantity is A1 power 1 over Q, etc. You mean these are the length of sides of the polygon?
Yeah, precisely. Yeah, I just say this briefly. I wrote in the beginning, form a triangle means side lengths of a triangle, and the same logic applies here. Yeah, thanks for the question. Okay, ready for applying this to our amoebas? So this allows us to do the following. We go back to the previous example. X is spectrum of R, where R is this coordinate algebra of 3 variables over C, divided by sum of the variables is equal to 0. Then the complex variety, the C points, can be simply written as the C linear homomorphism from R to C. That's something we know from algebraic geometry. But we can do the same things for the amoebas. That's a cool thing now. And this basically due to Vero just coming in new dress. So the A cube of X, the X again missing, this is equal to all triples ABC. So that the Q's root of them form a triangle. But this now really means that A plus B plus C is in the null set of TQ. So we can write something as 0 in this triangular hyperfield. And this happens to be equal to the C linear homomorphisms from R to TQ, where the C linear structure of TQ is given by this absolute value to the Q that we saw before. It's in C algebra. So this is an easy exercise, and we use in this exercise that the absolute value is surjective onto the reals. So, I mean, this says somehow this set here is realizable. It's similar to tropical varieties. There are tropical varieties that are not realizable and tropical varieties that are realizable. This goes into here. Let me not dwell more into the details. But the upshot is that, well, we have C linear homomorphisms from R to TQ. So this justifies by denoting this set by X of TQ. So the amoeba are TQ rational points of our complex variety. And this actually holds also for Q equals 0. So the tropicalization are rational points in the tropical hyperfield. And even better, the absolute value, which is mapped from C to TQ, defines push forward on these rational points just by post-composition with the absolute value, as in the usual sense. So we get an induced map from XC to XTQ, so taking rational points as functorial, just by this recipe, and this map agrees with the map that we had before from X of C to the Q amoeba, or tropicalization, in the case Q equals 0. So we get an algebraic geometry framework for this amoebas. Okay, so this was basically what Vero was working out in this paper.
Sorry, one question.
Yes.
This is here it's important and the variety is a linear subspace, yeah?
No, I've chosen an example just to make things more digestible, to don't have abstract formulas, but I've chosen this example on purpose because x plus y plus z represents sides of a triangle, so I want to link things. But this works actually for any equation. So instead of x, we could have x squared and some other monomials. We can have more degreed things, but then we don't have only triangles, but polygons that we need to worry about. So I just want to present one simple case which links.
It's not important that it's a line.
No, this is completely general.
Oh.
Yeah, thanks for the question. It's good to point out. Okay, as far as I know, Vero just worked afffinely or inside the torus. I didn't look this up, but nothing prevents us from creating band schemes, and then we can tropicalize arbitrary varieties. And, well, we need coordinates coming from embedding into a toric variety or some toroidal compactification or something like that. But we can go beyond the affine case. And I will not go into there, but I want to explain to you now one important example, which are Grassmannians, to come back to the main topic of this talk and apply this. So first of all, I explain what projective space is. And instead of saying what the band scheme is, let's step back. In usual algebraic geometry, we know what the scheme is if we know what it does as a functor of points. So we just need to know what are the rational point sets. So what I do here is I describe you the rational point sets. I don't explain to you what the underlying band scheme is, but I just define it as a functor from bands into sets. So what it does is, if we take a band, then the projective space, it's just the same thing that you know. It's n plus 1 tuples in B n plus 1. One of the coordinates has to be invertible, and then we divide out by the diagonal action of the units. The Grassmannian can be defined as a subset of the projective space in terms of Plücker coordinates, which satisfy the usual Plücker relations. So these relations come maybe in an unused shape, because normally if you index Plücker relation, you take wedges of vectors where you have an underlying ordering. I used unordered sets. So I have R plus 1 set and R minus 1 set, and then a sign which kind of relates back to the ordering of elements. The thing that you should note, which is new here, is we don't say the Plücker relation is equal to 0, which wouldn't make sense for a band because we cannot add things, but we say it's inside the null set. So there's a way to say that a sum of elements is equal to 0 by being an element of the null set. And that's the Grassmannian for a band scheme, for a band. The Grassmannian as a band scheme. So two things. First of all, if we do this for a field, so field is a tract is a band, we get back the usual Grassmannian over the field. So it's nothing new. What I said, these are really the Plücker relations just coming in a maybe unused shape. It's not the standard Beck's textbook presentation. The other example that I want to give you is a Grassmannian 2,4, which is defined by one Plücker relations that we know, which is the alternating sum of these three terms. And this whole band scheme is a functor from bands to sets that satisfies certain conditions that I don't tell you in this talk. Because it's... I can explain this afterwards. So, okay. So, let me check with time. Probably have to skip one of the slides, but I skip the last one, I think. So, I want to make a slight detour to really link this Grassmannians to matrices over triangular hyperfields, which show up in the title, because this is now put a little bit under the rug. But what I want to tell is that the Grassmannian is a moduli space of matrices. So this Grassmannian is a band scheme. So this is theorem. This is where I started my collaboration with Matt Baker, when we found out that his generalization of matrix theory actually leads to the Grassmannian being a fine modular space of matrix bundles over band schemes. Okay, I've not taught you what are matrix bundles. I will not do so, but you can imagine this is something like a vector bundle over a band scheme. More precisely, it's a pullback of the tautological bundle from the Grassmannian. So it's embedded in some product of the trivial bundle. So there's some geometry meaning, and that's maybe the right definition of a vector bundle in F1 geometry. And but one consequence, which will maybe speak to some specialists in the audience, is that if we take a tract, then there's a canonical bijection between the T rational points of the Grassmannian and T matrix in the sense of Baker-Bowler's theory of matrices with coefficients in tracts. Okay, I know that I haven't defined that, so let me give you two more concrete examples, which hopefully will speak to you. So two particular tracts are the tropical hyperfield. So if we evaluate the Grassmannian, the tropical hyperfield T0, then this is canonically bijective to the Dressian, which is a space of all tropical linear spaces, or valuated matrix. So the T0 points of the Grassmannian corresponds to tropical linear spaces, which is somehow what we use in classical algebraic geometry. The K points of the Grassmannian correspond to linear K subspaces. And the other one is just a counter check that usual matrices fall into the theory, and usual matrices correspond to the K rational points of the Grassmannians. Just a sec. Where K is a so-called Krasner hyperfield with elements 0 and 1 and a certain null set. It's not important for the talk. Just want to say that usual matrices fall into the picture. Yes?
Do you have topologies or some space structure on these band schemes so that these bijections actually become like morphisms of cone complexes or?
Cone complexes is a little more difficult, but we have topologies and their homeomorphisms. So this is based on the work that I did with Cecilia. As soon as a band has a topology, the rational point set gets topologized. And if we do topologize T0 just with a real topology coming from the order of elements, then this is homeomorphic to the Dressian as a tropical variety, as a topological space. Cone structures, yes, you can get this from the Plucker relation. This gives you a cone subdivision. But note that the Dressian, this is not a tropical variety, so it doesn't satisfy balancing conditions. So this is quite weird. But you can read out the subdivisions that exist for the Dressian from the defining relations. But this is something particular for the tropical hyperfield. So, yeah. Okay. Let me use the last 3 minutes to come back to our suspension arc, which now comes to conclusion. Namely, you want to realize the Lorentzian polynomials as matrices over triangular hyperfields. So here, just two definitions that I use for notational purpose. LRn are the Lorentzian polynomials for fixed R and n. And PLRn is a projectivization. So we kick out the 0 vector and divide by the diagonal scaling of positive reals. And, well, just to conclude what we have seen before and put this into the picture with triangular hyperfields, remember that polynomial f is a Lorentzian, I mean, for r equals 2, n equals 4, if and only if the three numbers here form a triangle. Okay, now you can add 1 plus 1. This forming a triangle means the sum of these three quantities is 0 for a certain triangular hyperfield. Well, square roots means exponent 1/2, so it's inside T2. So this means that L of 2, 4, these are all polynomials of this form, such that the Plücker relation here, remember -1 is 1, so the sign vanishes, is in the null set of T2, the 2 triangular hyperfield. And then if we look at the projectivization of L24, this is a Grassmannian over T2. And this gives an explanation to the theorem that I stated in the beginning of the first slide. And this is the most clean case that we can state, 2-4. Well, there are other examples, more complicated ones, but in general, if we go to, we increase n or r, then we get higher degree terms that define both sides of this equality, the Lorentzian polynomials and the Grassmannian, which differ. So there's a divergence of equalities. And the best that well, there's several things that we can say, but one good thing that we can say that these two spaces are still homeomorphic. So if we ask topological questions about Lorentzian polynomials, we can answer them by looking at the Grassmannian, which is a simpler object, because, I mean, I don't know how explicit I was. The Grassmannian is defined by Plücker relations, which are quadratic relations, and the combinatorics is quite well understood. So there are ways to deal with them. Lorentzian polynomials are defined by, well, their derivatives, which are not so bad, but their determinants, which, if you increase n, this will be very high degree relations, and this is very unwieldy. Even the case of 2, 5, it's already very hard to calculate, and we need to develop quite some theory to get a hold on that. And I think I skipped the last slide, but let me mention one application of that. Peter Brennan asked some questions about the topology of Lorentzian polynomials, and he proved for uniform matrix, which we have seen, I think, in Alex's talk, that well, there's something like an open cell and the closure of the open cell. Okay, I don't want to get technical. I think it's a whole Lorentzian polynomial. He proved that this is a ball. I hope I said this correctly now. But then you can ask the question of, you take a thin Schubert cell of just one matrix, of all the Plücker coordinates that correspond to one matrix, takes a closure inside the Lorentzian polynomials, and ask whether it's also a ball. And we can answer that it's not by kind of comparing the space of Lorentzian polynomial with something simpler and computing Euler characteristics. And turns out that for a certain matrix, the Euler characteristic is not 1. And we can show the same for stable polynomials. So Peter Brennan asked the same question for stable polynomials. And yeah, we have explicit examples where the space of stable polynomials, which form a subset of Lorentzian polynomials, do not form a ball. Okay, I think that's a good point to stop. Thank you very much.